Good to have you back. For this lesson, we're going to talk about Riemann sum is the second part of the area under the curve calculation. The first part I did, it was based on rectangular approximation. There were three different kinds that we did. I will put a link in the description below or put a card up here as a review that you may want to go back and double check. But that's what we're going to do. We're going to polish that off in this lesson. So Riemann sum, Bernhard Riemann, he's considered to be father of modern integration and is a German mathematician. Not only that, he's a huge influence in geometry, where actually Einstein used the idea of the curvature geometry to talk about his relativity. So if you just remember, we did this rectangular approximation. We did three different kinds. We did the left-hand side, left rectangular, right rectangular, and midpoint rectangular approximation to find the area under the curve. And we noticed that in the last lesson that the midpoint was the most accurate one, based on the fact that the number of subintervals, that means the number of rectangles that we created, were the same. They were never changed, right? But the idea was this, that as we change the number of rectangles, we notice that the area under the curve becomes more accurate and accurate. So look at this one. This one has got this graph, the first one, and then we're going to look at the second graph. The first one, we have the interval between 0 and 4, and the subinterval is 1. So delta x is 1. That's the width in between. So right there, okay, each of these are 1 unit. Okay, as you can see, 1 and 1 here, 1 there, 1 there, right? And we have the number of subintervals, 1, 2, 3, 4 rectangles, and that's 4, and that's very simple. Okay, so there are 4 of them, and we notice that there are areas of the graph that it has not been calculated for the area under the curve. So that's one of them, that's another one right there. So these little triangles here, including that area, and that area, including, by the way, because it's on the fourth, all the way up to here. So this area right there as well, because that's the point 4 right there. That's already, again, is not being calculated. The area under the curve is not there. So this is under approximating the value. But then you look at the second graph, which I graphed it here for you. You notice that I have chosen, in this case, 10 values, and the interval is between 0 and 4, but now delta x is 0.4. Okay, that means the distance or the width of each of these small rectangle, okay, each of these guys, the width of that is 0.4. Okay, and there are n number of subinterval is 10. That means there are 10 rectangles. And now you can see that the area under the curve is actually becoming more accurate. Okay, and that's what Riemann sum is basically is telling us that if we look at this specific idea, that if the number of rectangles approaches infinity, okay, so instead of having 10, now we can have, let's say, 1,000 rectangles being created under the specific curve within the given interval. And that means delta x, that means the width of each of the rectangle approaches 0, right? So as the number of the rectangles increases, obviously we are decreasing the width of that rectangle. And Riemann says that if that happens, you can get a very accurate measure of the area of the under the curve. Now I'd like to show you graphically using Desmos. This is actually was taken from Desmos as well, but I want to show you graphically how this works, and then you can see what is happening. So let's go to Desmos. So here is the Riemann sum using Desmos. you can actually go to Desmos, and then you go to this area right there, click on that, and then you can type in, just like what is happening here. You go to examples, and it will actually type in the Riemann sum, and there are many examples of that. I chose one of them, and I changed the functions that I wanted, and I got this. Now, I want to make sure that you see that this n is the number of subintervals. So the original interval we have is AB. So the AB was defined as 0 and 4. So here it is. This is 0 here, and this 4 there. So that's our original interval. We want to know the area under this curve in this specific interval. All right. So, and then based on this, we are going to use it for subinterval. That means that each of the delta x, each of these areas from here to 1, right there. So this is 1 unit, 1 unit, 1 unit. They're all the same. They have to be the same. Now, this is 4. Notice how much of this graph is not shown, or the area under the curve is not being calculated. This area right here is not being calculated. Okay, right here. So this is number 4 right there. So this is 4. Yes, it is. So all this kind of almost a triangle area right here is open, and that area is not being covered. But look what happens as I increase the number of n. That means the number of subintervals. Here it goes. Now it's 7. And then notice that what is happening. As I am increasing n, the number of subintervals or rectangles under the curve, the area in which this being covered under the curve is being expanded. That means it's covering almost every area under the curve. Now, this is just 11. Look what happens if I change it to 20, 21. Now, if I hit it more and more, you can see, if I zoom in, you may see, okay, there's still some gaps between the graph and the rectangles. Sure it is. But it is very, very accurate to a point where if we go to the max level, I put it in 100, but it could have been 1,000. So look what happens. Once I hit it 100, the calculation for area under the curve becomes super accurate. And if you change that to 1,000 or 1,000,000, and that's what Riemann sum is, where the number of rectangles approaches infinity. That means that the width of each of those rectangles approaches 0, and then you can get a very accurate measure of the area under the curve. Okay, so that is one of those things that I need you to play around with. Now, notice that in this example, I am using the left rectangular approximation, but it doesn't matter. So if we go back to our formulas, so I have 3 of them. So for the 3, we have the right hand approximation, and this is given by this sigma notation that shows the sum of all rectangles. So this is a sigma notation. Sigma is a Greek letter for sum. Okay, and the bottom piece is the lower bound, upper value is the limit or the upper bound, and then you have the argument, which is this f of xi delta x. That's the argument value, or we can call it integrand, but we're going to explain that later. That's the argument. And basically what he's saying is that is length times width. This is what that is. F of xi is your length. Delta x is the width of the rectangle for each one. Now this I is supposed to be there. Xi subscript I shows the all the initial intervals reference values, the sample reference values, right? So in this case, it's the right-hand side. This one is the left-hand side. That means that you are starting not at x0, but at x1. And then you have the midpoint. That's the formula for midpoint, where you have basically choosing the mid value and then choose a function at that mid value to get the length and then multiply it by the width. But regardless of which one you use, the idea is this. The idea is that as n approaches infinity and delta x approaches 0, both of these mean the same thing. We're going to have a very accurate value of the area under the curve. Okay, that's what this is about. All right, let's do an example on that now. Here's the example. Approximate the area under the function y equal to x squared, or f of x equal to x squared, on the interval 0 to 2, using n to be 4 subintervals, and use the right Riemann sum. You could have used the midpoint or the left, but we can use right, just that we're going to use one of those formulas, which is right here is given to you, and we're going to use the summation. So the very good idea is to rewrite what's happening and what is it we have. So first of all, delta x. Okay, let's find delta x, and that's given by this, or you can just say, okay, there are 4 subintervals between 0 and 2, so each of the subintervals delta x must be, so that would be 2 minus 0 divided by 4. That means each subinterval is 1/2. Great. So we have this subintervals x1 equals to 0.5, and x2 equal to 1.0, x3 equals to 1.5, and x4 is equal to 2. Now that we have this, we're just going to go ahead and plug numbers in there and do the summation. Remember, the sigma notation, you're adding all the areas of the rectangle that is given by f of xi times delta x. All right, so we're going to plug values in there and then come up with the final answer. Let's do that. So start with, so R4, that's Rn, is equal to, and then we're going to go ahead and start plugging the values. F of 0.5 times 0.5 plus f of 1.0 times 0.5, that's your delta x, right? So that's all we're doing here. We're just putting the values in there until the last term, which is the 4th term. We're going to add them all up. And when you do this, you'll get, and remember that f of 0.5, that is 0.5 squared. Now, the function we have is f of x equal to x squared. So we're going to grab this 0.5, plug it in there, so it becomes 0.5 squared. And that's what that is. Okay, I just wanted to show you one sample substitution, and then you can do the rest yourself. Okay, and that is equal to, when you add them all up, that is equal to 3.75 units. Whatever the unit is, that's the area under the graph of y equal to x squared, f of x equal to x squared, within the interval 0, 2. Now, this is obviously not very accurate, which is probably overshooting. So in this case, it seems that we can assume that this is one of the approximation, and if we increase the number of n, the number of rectangles, we can get a better value. All right, so that's all I want to talk about. Check out the next video where I'm going to change the idea of Riemann sum to the integral signature, and then we're going to go from there. All right, until next time.